Thank you very much. It's my great pleasure to speak here. I'd like to begin by thanking the organizers for bringing this very nice group of people together and having this conference, making this conference possible. So I'm going to speak about some inequality that's called divergence-curl inequality. There are two main themes in this subject. The first one is some kind of compensation phenomena that has to do with the divergence operator that we learned in multivariable calculus, the curl operator, and the space of integrable functions or differential forms, L1, which happens to be quite different from something that is called compensation compactness that people study classically. And then there's another theme that is somehow also at the background of all these things, which is the failure of some critical Sobolev embeddings into the space L infinity. For example, we know that if we look at the Sobolev space W1n, which is the space of all functions whose derivative is in Ln on Rn, those functions may not be bounded. And this is one thing that is also at the back of the subject. So what I'm going to tell you at the beginning will be a story that began something like 10 years ago. Some of the main contributors here will be Bourgain, Brices, Laura Dennon and Stanley here, Stein, and also Van Schaftingen. So we'll talk about these results in Rn first of all, and then towards the end I'll tell you a little bit about a subelliptic version of the same story, and that would be my joint work with Yi Wang, who is currently a postdoc at Stanford. All right. So let's begin. We'll work on Rn where n is bigger than or equal to 2. This is just a slide that reveals the differential complex on Rn. We remember that a zero form is simply a function on Rn. And if you take d of a zero form, this is almost like taking the gradient of a function. This is the differential one form given by these coefficients here. Similarly, a one form is something of the form summation ui dxi, where ui are functions of x. And if you take the d of a one form, you get the two form, and this is, if the dimension is equal to 3, this is almost like the curve of a vector field. In general, of course, d as a differential operator that takes a q form to a q plus 1 form, there's this expression here that defines the d operator. So there is this inner product on the space of q forms, and using this inner product, you can define a formal adjoint of this d, which is called the d star operator. For example, if you have a one form, then d star of this one form would be a function, and this function will be given by summation d ui of dxi, which is basically the divergence of a vector field. And if u is a differential form, I'm going to take the LP norm of this differential form by summing the LP norms of the components of the differential form. So just some very simple notations at the beginning. Well, we'll get to the main question that we want to ask right here. But just before that, I want to mention that the D forms are complex in the sense that if you take D of a differential form, then it's equal to 0. Similarly for D star. And these operators are related to the Laplacian by this expression here. If you take dd star plus d star d of a differential form, this is equal to the component-wise Laplacian of the differential form. And there's this Hodge decomposition, which tells you that if U is a Q form, which is, let's say, smooth with complex support, just to make life easier, then U will be d of something plus d star of something. In fact, U will be an operator acting on d star U plus an operator acting on du. So U is determined by both du and d star U together. All right. So the question that we want to ask is the following. If, in addition to these assumptions on U, we assume that both du and d star U are, let's say, differential forms that has integrable coefficients, we want to ask whether you can control U in LP for some P that is bigger than 1. This is like classical question that we ask in harmonic analysis. In fact, when Q is equal to 0, when U is a function, then we know that this is true, because if Q is equal to 0, then U is a function, d star U is 0, and then du will just be the gradient of U. So if you know the gradient of U is in L1, then you know that U will be in some LP for some P bigger than 1. In fact, P will be n over n minus 1, if you remember the exponent from the Sobolev inequality or the Gallardo-Liebenberg inequality. In fact, I've actually written down the inequality here. If U is a function that's moved with complex support on Rn, then the Ln over n minus 1 norm of U will be controlled by the gradient of U in L1 of the constant. And what we're interested in the next few slides will be what happens if the degree of the differential form is not 0, but let's say strictly between Q and N. Okay. So that brings us to the first result, very interesting result by Lansani and Stein. Suppose the degree of the differential form Q is not equal to 1 or n minus 1. Okay? Then U, if U is this, let's say, smooth with complex support, then we have this estimate here that says that you can control the Ln over n minus 1 norm of U by du in L1 and d star U in L1. Okay. Moreover, if Q is equal to 1 or n minus 1, then there's a modification of this inequality. The inequality as stated will be false, but if you replace, let's say, d star U in L1 by d star of U in Hardy-H1, which is a smaller subspace of L1, then the inequality will remain true. Okay? Similarly, if Q were equal to n minus 1, then you replace du in L1 by du in Hardy-H1. Okay? So there's one result that is, I think, 8 years ago, in 2005. Since d star of a function is always equal to 0, when Q equals 0, this is again just the Gallardo-Liebenberg inequality as we have just observed. On the other hand, if you have Q equals 1, meaning that U is in one form, then du is basically the curl of U, and d star of U is like the divergence of U. So this is sometimes called a divergence-curl inequality when Q is equal to 1. Now it turns out the proof of this is actually quite elementary. I mean, it's very beautiful, very tricky, but very elementary. And this is along the lines of Entschärftingen that Lansani and Stein gave in the paper. On the other hand, Bourgain and Brices has a proof of the same inequality using a completely different proof. So first of all, they observed the following. For any function f that is in Ln of Rn, there exists a vector field y with bounded coefficients so that the divergence of the vector field is equal to f. Well, the divergence is taken in the distributional sense. Okay? With the property that the L infinity norm of y is controlled by constant times f in Ln. Now, you can always find such y. You can always find a y with one derivative in Ln by Hodge decomposition. But if you take a y that is in W1n that solves this equation, since W1n don't embed into L infinity, this is not going to give you a solution that is in L infinity. On the other hand, the upshot is that the system here is underdetermined in the sense that if y is a solution to this equation, so is y plus any divergence-free vector field. If you take y and you add to it a vector field with divergence equal to 0, you still have a solution. The claim here is really that you can find a solution that is bounded by adding a divergence-free vector field. So you want to add something with divergence equal to 0 to this equation, and then you can change the solution so that it becomes bounded. In fact, there's a corresponding generalization of this estimate to the equation d star y equals f, where y would now be a q plus 1 form and f be a q form, as long as the degree of f is not equal to n minus 1. Moreover, the proof of Bourgain-Bricy shows that the solution y here can be chosen not only in L infinity, but in a better function space. It is going to be both in L infinity and in W1n. If you only want one of them, we saw that it is possible. If you want it to be in both, this is also possible. And this in turn leads to an improvement of the inequality about the du and d star u, given by Lensenius-Stein. But that's a little bit more complicated, so I'm not going to state it. So this is the last thing I want to say about what happens on our end. The proof of Bourgain-Bricy is constructive and makes use of the following approximation lemma, which is a very fundamental statement, which I think is of independent interest. It says that for any positive delta, you can choose some constant c delta, so that for any function f in W1n, you can find a function capital F that is both bounded and in the subelliptic space, for which the following is true. If you compute the ith derivative of little f and compare it to the ith derivative of capital F, as long as I is not equal to, let's say, 1, so as long as I is from 2 to n, this is not a typo, by the way, you can control this in Ln, and this is going to be very small. For any small delta, this is going to be very small. And, well, the last statement simply says that when you say the f is in L infinity and W1n, then the norms are controlled by corresponding data, which is gradient of f in Ln. So it says that capital F approximates the derivatives of little f in all but one direction. So I think this is the only connection I can make to extensions or approximations in this talk. But at least there's some big connection here about subelliptic spaces and approximations of functions in this particular critical subelliptic space. So, well, in joint work with Yuan, what we've done here is an analog of a certain approximation lemma of Bourgain and Bricy, not in Rn, but on something called the Heisenberg group. The Heisenberg group here is a non-abelian Lie group that is diffeomorphic to the complex n-dimensional space product R. And there's a group law that is given as such. There is a natural homogeneous dimension on the Heisenberg group, and there's equal to 2n plus 2, and I'm going to just denote it by Q for convenience. Instead of telling you what the exact approximation lemma we have proved, which would involve a little bit more setup, I'm going to just say one thing about what we can prove using the approximation lemma, and that is a kind of Galiardo-Lierenberg inequality for something that's called the d bar B complex on the Heisenberg group. So there's some complex analysis. There's a complex analog of the differential operator D in several complex variables, and it's called d bar B. And well, this is an estimate that we can prove that is along the line of Lensenius-Stein. If U is a COQ form on the Heisenberg group, where Q is between 2 and n minus 2, then as long as you control d bar B of U in L1 and d bar B star of U in L1, you will control U in a certain LP space that is bigger than 1. In fact, the exponent is given by this homogeneous dimension here, which is the natural one. Furthermore, if you look at functions, as long as n is bigger than or equal to 2, then you can control you can control U in this function space LQ over Q minus 1, as long as d bar B of U is in L1. And if U is orthogonal to the kernel of d bar B, because d bar B here is going to have a kernel, same result hold if you have a CON form, etc. There's also a corresponding result that says that you can solve a certain underdetermined systemification that's called d bar B star of y equals f, etc. But I think for the sake of time, I'm not going to go into that. So is that all the time that I have? Okay. So I think I'll stop here. Thank you very much.
Yes, please. Have you looked at doing the same sorts of arguments
Well, we don't really need d bar b, but on the other hand, if you look at the d bar on the domain, then, well, first of all, there's the question of the elliptic analog of all these things. If you look at a domain in Rn, you want to ask whether you can have an inequality of this kind, right? So that turns out to be something that is relatively easy when if you don't care about exact constants, there's something that's relatively easy from all these considerations. And a similar story would hold for d bar. I think if you want like an estimate for d bar instead of d bar b, then a similar thing can hold as long as you use the elliptic story. I think that is not too hard. So that turns out to be, I think, doable. But I don't know. So the d bar b is slightly more interesting.
So you want to, I mean, of course, the issue with d bar is, right, being in the domain of d bar star. I mean, of course, with U and C being compact, with compact support, of course, it would.
Right. Then it wouldn't be an issue, right?
I mean, is the compact support essential to?
No, this is actually an a priori type estimate. The compact support thing can be getting rid of. It is not really the essential part. So, right. But that's a very interesting question. We want something to be in the domain of d bar star. And, right. Yeah. By the way, if I could mention one open problem here, since I just saw this inequality and remember this. There's this isoperimetric inequality in Rn that's equivalent to the Gaudiano-Liebenberg inequality for functions. That is when q is equal to 0. So that's a very geometric inequality. And one natural thing that one should ask, for example, is whether there's a geometric interpretation of this inequality for differential forms of degree higher than 1. I really don't know. So take n equals 4 and q equals 2, for example. This is a very simple inequality. Is there any geometric meaning to this inequality? And if there is, then the best constant here could be very interesting. That could be some kind of higher dimensional isoperimetric constant that one would want to look at. But I don't know anything about this. And some of you have any idea about this, then I would be very grateful to learn about it. Thank you very much.